Tohru MORIMOTO from RIMS, who will talk about differential equations associated with representations of the algebra and the extrinsic geometry of submanifolds in a flag manifold.
Thank you. First of all, I'd like to express my gratitude to the organizers. Okay. So, the title of my talk is this. Okay. So, what I'd like to talk is the very intimate relations between real groups and differential equations and geometric structures. So that is, there is very close relations between linear differential equations and extrinsic geometry in flag manifold. Okay, so flag manifolds, very generally flag manifolds, but project space or Grassmann manifold is also the special case of flag manifold. And okay, so very close relation between these is especially so for each representation of real algebra, we can associate a class of linear differential equations, and for the study of these differential equations as equivalence problems is very correspond to the extrinsic geometry of flag manifold. So this relation can be very well understood with that we call nilpotent geometry and nilpotent analysis. Okay, that is what I would like to talk in this talk. Okay, so for that, first to explain what is nilpotent geometry and analysis. Okay. First of all, I'd like to explain the notion of filtered manifold. Filtered manifold is a manifold equipped with filtration. Filtration on tangent bundle, which satisfy the following three. Do you have some bars or something? Something. Yes. Ah, yes. Okay. So push. Okay. Satisfying the three conditions. First of all, FP is subband of the tangent bundle, and secondly, the filtration is descending, starting from the tangent bundle to 0. So, in particular, in our notation, the filtration is negatively concentrated, okay? And the bracket of the section of FP and the bracket of the section of FQ is contained in the section of FP plus Q. Okay. Here, underbar denote the sheaf of the germ of the section of the vector bundle FP. Okay. So this is a very natural conditions. So I say filtered manifold, the manifold equipped with the filtration satisfying these conditions. Okay. So of particular importance is that to each point x we can associate the graded object. Okay, So graded object is obtained by simply taking the gradation. Okay. So fx denotes the fiber over x of the f. Okay, and group P fx is defined to be the factor spaces, and the group fx is the vertical sum of the group P fx. So it is of course the graded vector spaces. But what is important is that it is not only the graded vector space, but it is endowed with real algebra structures. The bracket is defined from the bracket of the vector field. So a little more precisely, bracket of Gz in group P fx and ether in group Q fx is defined in this way. Okay, where x and y is, we take the representative as vector field x and y. Okay, in this way. So this definition does not depend on the choice of x and y. Okay. So the bracket group P fx is defined as the point, not depending on the how to say so only the value of the Gz and ether determine the bracket. Okay, that is important point. So at each point we have graded nilpotent real algebras. So at each point of a filtered manifold, we have graded nilpotent real algebra, which is called also symbol algebra of the filtered manifold at X. Okay. So example of filtered manifold. Trivial filtered manifold. So f minus 1 is tangent band itself, and f0 equal to 0. Then it is filtered manifold. Okay, trivial filtered manifold. And of course, in this case, group fx is nothing but the tangent space itself regarded as the abelian real algebra. So okay, so trivial filtered manifold is filtered manifold with the symbol algebra as abelian trivial graded real algebra. Okay, so next examples is take M is the three-dimensional Euclidean spaces with coordinates x, y, z, and tangent band is, I write f minus 2, and f minus 1 to be the subband of codimension 1. Okay, so omega f minus 1 is defined by omega equal to 0 by one form omega. Okay, and f0 to 0. Okay. So then, for any omega, okay, so f minus 1 and f0, okay, satisfies the condition that I described before. Okay, so it becomes filtered manifold. But the associated graded algebra is if omega is defined foliation, that is omega d omega equals 0. Okay, in that case the bracket becomes trivial here. So symbol algebra of f at x is always abelian graded real algebra. Gradation is non-trivial, but real algebra structure is trivial. And if omega defines the contact structure, in that case, f minus 1 to m bracket is not contained in this one. Okay. So in that case, this graded real algebra becomes isomorphic to a Heisenberg real algebra. Okay. So this is the symbol algebra of our MF. Okay. So we have many examples. Okay, but now we only cite these examples. A very interesting example in the also 5-dimensional space in rank 2 distribution, but I skip. Okay. So in usual calculus and differential geometry, so first order approximation of the manifold is tangent bundle, which is abelian real algebra. But when we start with filtered manifold, first order approximation of at each point x is we regard as graded nilpotent graded real algebra. That is a different point, starting point. Okay, and from this point of view, we study the geometric structures on filtered manifold or differential equations on filtered manifold. That I call nilpotent geometry and or nilpotent analysis. And nilpotent geometry was initiated by Tanaka and studied by himself and myself and Yamaguchi and etc. Okay. And also nilpotent analysis was initiated by myself. So to study the differential equations on filtered manifold, the fundamental starting point is what I call weighted order of differential operators. So I explain rapidly this. So given a filtered manifold, so I define a weighted order on vector field on MF to be the weighted order of x is equal or less than x if x is section of f minus k. Okay. Because of our filtration is negatively concentrated, I changed the sign. Okay, here. So the vector field x is called weighted order of x is less than x if x is a section of f minus k. Okay. And for the differential operator like the x1, xl, okay, I call the weighted order of p is less than the sum of all xi. Okay. So it's in this way we have well-defined notion of weighted order on the differential operators on MF. Okay, so this notion of weighted order immediately give rise to the notion of weighted jet band on the filtered manifold. Okay, that is so. Okay, if we are given vector band on a filtered manifold MF, but I prefer E is also filtered to be filtered. That is, E is vector sequence of vector bundles such that E itself is E nu 1 and E nu q and nu q etc. Okay, so E is filtered vector bundles over MF. Okay. Then for this filtered vector bundle, we can define the notion of weighted jet bundle of weighted order K. It's very naturally we can define the notion. Okay, so the weighted bundle is very canonically defined by defining some filtration of each fiber. Okay, but rather so this is a precise definition of the each fiber. Okay, but I rather give you the coordinate of the weighted jet bundles, which will help you to understand immediately what is the weighted jet bundles. Okay, so I just indicate what is the local coordinate of the weighted jet bundles. So the local coordinate of the weighted jet bundle is x1 to xn. This is the local coordinate manifold. Okay, and large xi uj at x. Okay, this and where wi plus j is less than k. These constitute the coordinate of our weighted jet bundle. Okay. This is not necessarily independent. Okay, but okay. So I now explain what is xi and uj. Okay. So uj. Okay. First. So our E is filtered vector bundle. So locally, it can be trivialized as a product with the vector spaces. Since E itself is filtered, we're taking the complementary subspaces. We can regard it as a direct sum of these vector spaces. Okay. So filtration is starting from here and next here and here like this. Okay. Then, so the section of E can be expressed as a function of M as u nu 1, nu I, 2, nu j, etc. Okay, as a section of vector varied function of this is vector value here, taking values okay here, okay, in this way. So this uj is functions, vector varied function j, okay, indexed by the decomposition of this. And x large I is a multi-index. Okay, so x like this. Here x1 to xn is admissible local basis of f. That is the independent vector field on the filtered manifold such that x1 to x, this number is or rank of fp is local basis of fp. Okay, so I take the basis vector field from as the basis of each fp. Okay, in the order in this way. So then, I can define the weight function of 1 to n to 1 to mu. Okay. Mu is the depth of the filtration, okay, such that to each xi is the section of f minus omega I. Okay, so in this way, so w is our weight function, and for this xi, I is multi-index. Weight of w capital I is the sum of omega IA. Then so weighted order of this differential operator xi just wi. Okay. So in these notations, the local coordinate of our weight jet bundle is nothing but this the local coordinate of M with xi uj. Okay. But here, of course, this differential operator have some commuting relations. Therefore, so this xi uj is not independent, but it's this value of here and here determines the point of our weight jet bundle. Okay. So so it must be very clear. So what is the weighted jet bundle here? Okay. So after defining the weighted jet bundles, any differential operator on the filtered manifold of weighted order k can be written as in this way. So the submanifold of some weighted jet bundle Rk0 can be regarded as a system of partial differential equations of weighted order K0, okay, on filtered manifold. Any differential equation on filtered manifold can be regarded as a submanifold. Or so this can be locally written as 0 point of these equations. Here, xi uj is order less than k0. Okay. And so phi is some vector valued functions. Okay. So that is most general system of differential equation on filtered manifold. Okay, so to study the differential equations, first important notion is prolongation.
Weighted
Yeah.
jet bundle covers eventually all the partial derivatives.
Yes.
So there are certain non-degeneracy.
No conditions. So any differential equation is regarded as a submanifold of weighted jet bundle. Okay, and if you want it to be linear, so it's as a subbundle. Okay, if our R0 is subbundle, then so it is a subbundle. Then it is so linear equation. So given a different equation phi, so we have a notion of formal derivatives. That is, for xl we define xl phi like this. Something is maybe something wrong, but something very usual notion of prolongation is easy to define. Okay, so given Rk0, we can define the prolongation of this equation, the k0 plus l to be the formal derivative or variation derivative of phi with respect to xl, with the weighted order wl is less than l. Okay, so we have the notion of prolongation of differential equations. So it's rather convenient to consider the differential equation as a sequence of differential equations, okay, like this. So if you only give a finite number of differential equations, we only put Rk equal just trivial to be jet itself for k large enough. Okay? So we suppose we are given a series of differential equations. We can define the prolongation of R, okay, as the like this, or the intersection of the prolongation of RK, etc. Okay. So the notion of prolongation is very easy to define. Then, so for R, given differential equation R, RK, is integral is it means that is nothing but the prolongation of R contained R, and each RK plus 1 to RK is surjective. Of course, this is infinite number of conditions, and so to have criterion for this integral homointegrability is also important things. Okay. But later I just very rapidly mention this. And another thing very fundamental is notion of the symbols. So first of all, I say that we have this fundamental exact sequences. That is, there we have a natural prediction of jk to jk minus 1. So what is the kernel of this projection? It is written like this. Okay. Here, group E is associated greater vector bundles here, and U group F. So U is group F at a point is, as I mentioned, nilpotent B algebra. So I take the universal enveloping algebra of this nilpotent B algebra, which is this is naturally graded, and therefore U itself is graded. Okay. And therefore, so we can speak of the element of hom to this of degree, homogeneous degree k. Okay. So it is all the element of homogeneous degree k consist to these spaces. And this is the kernel of this projection. And this is just very parallel the well-known exact sequence of these two one. Okay. In this case is if the usual jet bundles, then in that case is the kernel is as well known is symmetric tensor product of a cotangent bundle. That is nothing but can be regarded as this symmetric tensor spaces to E. And this is exactly the enveloping algebra of the abelian nilpotent, abelian real algebra. So this is a very natural generalization. Okay. Okay. So
on the E, the bracket is compatible with the
pardon?
bracket. So on E,
Yes.
we have bracket, right? The filtration. And then now, is it compatible with the bracket on Hamilton space?
Group E is only the vector space, only the vector bundles. So it is group U group F is universal enveloping algebra. Okay. So regarding as graded vector spaces, we have homomorphism, okay, of degree.
Or E,
Huh?
I'm asking like E is like E has going.
No. E is only a vector bundle. So you are given filtered vector bundles over filtered manifold. Okay. So group E is only the graded object of the filtered vector bundle. Okay. So with this exact sequence, we can define the symbol of the given different series of differential equations. Okay. Then we can define the symbol of R to be the kernel of this map. Okay. So our symbol sigma k is contained in these spaces. Okay, so I denote by sigma to be the symbol of R. Okay. Now, so the fundamental thing is that if the prolongation of R contains R, then our sigma, the symbol, is U good F. It is nilpotent real algebra. Oh, it is real algebra. Okay, universal endogenous algebra, and it is U good F right module. Okay, it is the first important things to study the differential equations. Okay. Okay, so and also with the differential equations, there is big difference of finite type and infinite types. So I say that if sigma symbol vanishes at some order, okay, then we say R is finite type. Otherwise, it is called infinite type. Okay. And finite type and infinite types, yes, so there is big difference. The finite type equation is essentially reduced to, in a sense, ordinary differential equations, and the infinite type case is not. So, given differential equation, so first thing to study will be the existence of solutions. Okay. So for that, the formal integrability or also analytic solution problem is very interesting problems, and we can study very well these things in the category of weighted jet bundles, and we have very nice generalization of Cartan-Kehler theorems. But here I don't enter into discussion of this existence theorems, but rather we discuss the equivalence problems of differential equations. Okay. So that is given two differential equations. The two equation, if these equations are equivalent or not, is very interesting problems, especially when R is finite type or overdetermined systems. In that case, it's very interesting problems, and that is now I'd like to discuss. Okay, so
Equivalence means
yeah.
yes,
Yes, in many contexts you can discuss. Okay, so in some cases you can discuss point transformation or contact transformation, or more Becklin transformation may be also interesting. Okay, and also just now what we are speaking of is the linear differential equation. Okay, in that case we equivalence problems under some transformation which preserve the linear equation to linear equation. Send okay. So the equivalence problems, there are various way to treat. Okay, depending on your purpose. Okay. Okay. So okay, now so first. Now I'd like to speak about differential equations associated with the representation of real algebra. Okay. So more precisely, so we'll consider graded real algebras, which I call transitive graded real algebra. Okay. That is the graded real algebra, first of all, and secondly, the negative part of G is finite dimensional, and with the transitivity conditions, that is if X is in Gi and I is non-negative, and bracket with X and G minus equal to 0, then x should be 0. This is the transitivity conditions. So I consider grade 3 algebra satisfying these conditions. By the two conditions, our homogeneous component GP must be finite dimensional. Okay. But and so negatively it is finite dimensional. But G can be infinite dimensional in the positive direction. Okay. So G, in many cases now we are considering G is finite dimensional, but we can also consider the infinite dimensional G. And V is G module, okay, the representation space of this D algebra, and the gradation is compatible in this sense. Okay, GP and VQ is V plus Q, and each dimension VQ is assumed to be finite dimensional, and there exists nu I such that VQ equal to 0 for Q smaller than nu I. And the fourth condition is similar to the transitivity conditions. That is, there exists nu T such that if Vj is contained in Vj and G minus Vj equal to 0, then Vj equals 0. Some condition of something, condition of effectivity. Okay. Okay. So to this given Lie algebra and representation, so given the G and V, then negative part G minus is a nilpotent Lie algebra, and of course V is also the G minus module. Therefore, we can consider the cohomology group of the representation of G minus on V. That is the cohomology group of the chain complex of G's. Okay. This delta is defined as usual. Okay. Then we have the cohomology group, this one. This map is degree preserving R. Okay. So our cohomology group is by degree, have by degree P and R. Okay. So also I note that these cohomology groups has because of the Noetherian properties of enveloping algebra, so it vanishes for each P large enough R. Okay, even if our G and V is infinite dimensional. Okay, so this cohomology group. Okay, so very symbolically, I can say that the cohomology groups H1 G minus V H1 defines a class of differential equations. That is, given representation of G and of V, then your cohomology group H1 is in some sense defines a class of differential equations. So okay, so a little more precisely, given G and V, okay, I write the class of differential equation dE. Okay. So the differential equation RK defined on filtered manifold as a subbundle of JKE, or submanifold of RK is the class determined by GV is defined by these conditions. Okay. So this is the condition. This condition is the definition define the class of differential equation of type GV. Okay. So it's not so very clear, but okay. So first of all, the first condition says that filtered manifold is of type G minus. That is, at each point, GUR fx is isomorphic to the negative part of G. Okay, that is our G, given G determines the symbol of MF should be G minus. Okay, so our equation is defined on filtered manifold of the type G minus. Okay, and the second condition says that on filtered manifold MF there is also given G0 structure. That is not only the filtered structure but also some geometric structure on MF. For example, so CR structure is underlying contact structure plus some geometric structure. That is on the filtered manifold we are given G0 structure, some generalized G structure. Okay, I don't enter into detail, but okay. So G0 is the real algebra of G0 is G0. Okay, that is G0 is the zeroth component of our G. Okay, so here first condition and second condition is the condition on the filtered manifold that our differential equation defined. And the third condition is about the unknown function. The differential equation is defined on JK, but so filtered vector band GUR E is isomorphic to P0 product W, where W is a subspace of V defined by V nu 1 to nu t. This nu is the number that appears in the definition of V. Nu 1 and nu I and nu t is this condition. Okay, so our equation GUR E is isomorphic to this is W is of course G0 module, and so we can take a product of fiber product here. Okay, so this is third conditions, and fourth condition. This is essentially what is most important to determine our differential equation. Our differential equation K, also K is larger than R1. R1 is cohomology groups that vanishes. Okay, so and the symbol of RL, where L or less than K less than L less than K is defined by the projection of RK to K. Then the important condition is the symbol of RL is isomorphic to VL. That is, very roughly speaking, the equation, our equation RK is defined by to be the symbol type is VL. Okay. So to say that VL, the symbol type of VL, our VL is in some sense we regard VL is contained is some these species. Okay. It's naturally we regard VL is contained in this one. Okay. This is something already some algebraic abstraction of the symbol. Okay. of Z spaces. And VL, we regard VL is contained in these spaces. And VL itself is, this is almost the definition of HIL. Okay. So we read this as the VL is defined by these cohomology groups. Okay. So,
Professor,
yes.
does it say VL is contained in HOM of
Pardon?
VL is contained in HOM of UG minus or
Yes. Yes.
UG minus?
Yes. Home UG minus. So
Universal.
universal empirical algebra.
Thank you.
Yes. So we regard VL in this way. Since VL is a kernel of this one, okay, so it can be naturally regarded as contained in this one, okay. So in that sense, VL is a subspace here. Okay, so the symbol of RL is isomorphic to VL. We have spoken of this statement, okay, by this. Okay, so some example, okay. So if we take the SL2R, the polynomial of homogeneous degree M, okay, symmetric tensor, then in that case, I very rapid, okay. So the cohomology groups becomes like this, okay. So it's our differential equation, associate class of differential equation, nothing but the ordinary differential equation of order m plus 1.
Linear or non-linear?
Pardon?
Linear or non-linear?
Non-linear or linear, okay. Any, okay. Non-linear, okay. Non-linear. So if you take the SL2, the representation SM, then it is this ODE of order m plus 1, okay. And next example is okay. If you take SL3 of the R3, we have a standard representation, and SR symmetric tensor, okay. And R3 dual is the dual representation, and we take the symmetric tensor S3, okay. Then so our SL3 is regarded as the grade real algebra in this way, okay, by taking the Borel subalgebra as isotropy subalgebra. So 0 means G0 here, and this 2, G2, and G1, and G minus 1, and G minus 2. This gives a great structure of our G SL3, okay. And moreover, we have canonical decomposition of G minus 1 to this component and this component. I denote my G minus 1 X plus G minus 1 Y, okay. Here in this case it's only one dimensional, both, okay. But we have a canonical decomposition here. Okay, so our filtered manifold is this SL3 factored by Borel subgroups. Okay, so we have in this three-dimensional space we have coordinates x, y, z. Then so this manifold naturally endowed with contact structure given by this, okay, by this contact form. Then I write the vector field x like this and y. It is a vector field contained in the contact structure. Okay, so in this case, if I denote V is three-dimensional vector spaces, and we decompose this component and this component and this component. So this I denote V0, V1, V2. Okay. And the dual space is as V0 prime, V1 prime, V2 prime, okay, in this direction. Then so I take the symmetric tensor of V and the symmetric tensor of V prime, okay, and I take the irreducible component of this, okay, determined by the highest weight of the standard representation of V and dual representation, okay. So the first cohomology group of our G minus on this V children is like this. Okay. This is on isomorphic to S plus 1, G minus 1, X, and to this. This is one dimensional. Okay. This is one dimensional. And so this means that our differential equation is of this type. This is our X and Y. Okay. And this here means the lower order terms than here. Okay. So this system of differential equation is, we know without computation that it is finite type differential equation. And dimension at most, the solution of dimension of the solution is at most our dimension V children. Okay. So in this way we obtain the overdetermined systems, finite types, and from the representation here. Okay. Okay. So in this way we have many finite type differential equations starting from any representation of a real algebra. Okay. So okay, so so the first thing I'd like to say is that the linear integral finite type differential equation and some embedding or submanifold of filtered manifold into the Frog manifold is in some sense, in a sense, nice one-to-one correspondence. That is linear integral linear finite type differential equation, and the not necessarily embedding, but with some slight condition, okay, related condition. It's embedding, okay, embedding of manifold into a Frog manifold is a correspondence, okay, and also okay, and also the equivalence problems of the linear differential equation is reduced to the equivalence problems of the embedding in the Frog manifold. Frog manifold, you have general linear groups act as transformation group preserving the geometric structure of Frog manifold. Okay. So the extrinsic geometry here correspond to the geometry of the linear equivalence problems of the linear differential equations. And Frog manifolds, so if we have our E is filtered in this way and rank is this one, then so our S star is take the S is the solution space of the differential equation, and S star is the dual spaces, and the number of Frog is determined by this rank of E0, E1, etc. Okay, and this the study of differential equation, study of submanifold is the reduced than the study of the oscillating spaces to each submanifold. We can associate the oscillating spaces, and these oscillating spaces and submanifold and differential equation are very tight correspondences. So in the special cases, it's projective spaces for Grassmann manifold. So I just say how the correspondence is when the case of for simplicity the case of Grassmann cases. So Grassmann case is if so for simplicity our filtered vector boundary is filtration trivial, okay, and then so our V is V0, V1, VQ, etc. And V0, we take W equal V0. Okay. Then so consider the differential equation and of finite type, and let S be the solution spaces. Okay. Since we are assuming that the equation, the solution dimension of solution space S is the same as the dimension of V. Okay. Then for each point X, we associated annihilator of Sx0 in the dual spaces, where Sx0 is section of S which vanishes at X. Then so with some natural conditions, so this dimension is equal to the rank of E0. Thus, we have mapped from MF to the Grassmann manifold. Okay. So this gives correspondence with the equation and the submanifold of Grassmann manifold. And oscillating space is defined by take phi x is E1 to EM. It is moving frames of the in V. Okay. And we take OX minus K to be the derivatives of Xi with respect to Xi. Okay. Then so we have a series of oscillating spaces, and this oscillating spaces is isomorphic to R K for K less than K0. Okay. In this way, so we have nice correspondence between the linear differential equations and submanifold in the Frag manifold and oscillating spaces. So and so the equivalence problem of linear differential equation is just the extrinsic geometry in the Frag manifold. So okay, so I just finished output. Okay, so when so equivalence problems of the when G is simple or semi-simple, okay, and V is say irreducible, then the equivalence problem of this can be completely solved with method of moving moving frame bundles, and with algebraic harmonic theories. That is, under the assumption G is semi-simple, we can, in principle, obtain of the complete invariant of the differential equations. Okay, so in the very simple case, simplest case is the ordinary differential equation, which was studied by Laguerre Forsyth and Wilczynski. And then, so it was generalized by Seashi and also Sasaki, Yamaguchi, and Yoshida. Okay. And then, so in a most general way, this was done by Dubrov and Machida and myself. And with this generalization, we are very general and very transparent way how to obtain the invariant of these differential equations associated to the representation of real algebras. Okay, it's